Thank you. Thank you, Alexis. Thank you, Lucilla, and thank you for the team of CEREGE for inviting me. It's a great honor to start this symposium. So as Alexis already said, I've spent quite a lot of time in my life on this critical zone initiative. And I want to show you today some of the main aspects, which I think is a new paradigm for earth sciences that can be really interesting to link earth sciences with societal problems, because as you know, there's no need to spend too much time on that. We're living in a period of the earth planets, which is a little bit dangerous. So today I'd like to talk about different things. If I have time, I'm going to define what the critical zone is, where does it come from, this initiative, talking a little bit about the scientific challenges. Why is it so difficult to get a view on this critical zone thing? It's a zone which is critical for humans, and this is where I think that geology and earth sciences are important to be part of it. How we get organized, and this is not an easy task, and then I will finish quickly by the European dimension, which is what is taking most of my time, I should say, right now. So, to start with the definition of the critical zone was proposed by the US National Council in 2001 to denote, I quote, the zone, the continental skin of the Earth, the zone which is comprised between the rocks and the sky. This is the zone of the planet which is habitable. This is the zone of the planet where life is, at least on continental surfaces, and which is very critical to understand as a system for our future, because this is where society lives. It's a mix between different entities, compartments that exchange matter and energy. It's a concept which is basically terrestrial, but it could be well expanded to the ocean, and we can discuss on that later. And of course, this critical zone is specific to the Earth. There is no other planet in the solar system which has a critical zone, meaning that thin pellicule which has been transformed during the history of the planet, the geological history of the planet, by different forces. So this is a bad representation, and actually we're working on getting new representation of the critical zone. But this is a bad representation, a vertical, let's say, a representation showing you what are the different compartments that can be associated with this critical zone concept. It's taking into account the ecosystems in the usual sense, but also the arable soil, the geological soil, because as you know, and in particular in CEREGE, soil is a notion, is a concept which is extremely diverse depending on the communities that you're talking to, but the water is also part of the critical zone. So the critical zone is not a concept which is separating the solid from the gaseous, from the aqueous forms. Everything is, all these compartments are together and linked together by transformations. The rocks are part of the critical zone, and this is where geology comes into the play, that in order for the planet Earth to get a critical zone, you need to transform what was originally rocks into something which is soft, something which is porous, something which is able to contain water and life. But the critical zone has not only a vertical dimension. It's not another definition of the soil. It also has a lateral extension. This is another bad representation, which is the key representation that we're using for the Oscar network that I will talk about later, which is the fact that when you're living here in Camargue, I don't know if I can use, this. In Camargue here, you depend upon processes which are happening here in the highest part of the Alps, because everything is connected laterally. And the main agent of connection is a water cycle, which again is a specificity of the planet Earth. And it's very important to have this narrative that the water cycle, which is specific to the Earth, is possible because two big energy sources meet on Earth. On one side, the solar energy, which is activating photosynthesis, which is warming the ocean and providing the evaporation of water, which is going to create the water cycle, but also, and this is very important in the way we tell the story, the deep earth energy is creating the reliefs. It's creating basically the continents in the earth. It has created the continents in the history of the earth. It's creating the slopes. And if the earth would have been flat, the water cycle wouldn't have been activated. And so the critical zone would not exist. So this transformation, my point today is to say that in order to get this zone at the surface of the planet, which is in which life has developed on the continents, you need to have both ingredients, the solar energy and the deep earth energy, plate tectonics, that create the critical zone. And of course, in terms of energy, it has nothing to see, and I'm not going to explain to you what that the solar energy, the amount of energy that the Earth receives from the sun is much, much higher than the amount of energy that the mantle cooling is creating. But on the geological time scale, both sources of energy are important and are responsible for creating the critical zone at the surface of the planet. So what is interesting when we want to explain how the critical zone on the planet was formed is the interaction of the water cycle, which is quickly summarized here on that figure, with the rocks. And there are a number of transformations, and I'm not going to go into the details today, but my favorite one, as Alexis said, I've been spending my life on studying chemical weathering, is this chemical weathering reaction, which is a really interesting reaction, which is summarized here, which is basically the reaction of atmospheric CO2 and water with the rocks. It's consuming the CO2, and it's a neutralization reaction that produces ions, dissolved ions, which are ultimately delivered to the ocean. It's forming clays, in particular, because some elements like aluminum or iron are not soluble and are not able to be transported to the sea. And I want to mention this scientist from the 19th century, which is basically unknown, but whose name is on the Eiffel Tower, not because he discovered this process of chemical weathering, but he was the first in 1945 to publish a paper, which basically was not read by the geologist at the time, saying that chemical weathering was a process consuming CO2 from the atmosphere, creating the soil, the clay, the kaolinite, and providing the nutrients to the ecosystem. So basically, this guy was a pioneering scientist that should be better known. And so the result of that, in particular, that chemical weathering process is to create at the surface of the planet a thin pellicule, a thin zone, which is not that thick, in which the rocks, which are here, and which are supplied to the surface by plate tectonics, are being transformed into something which is porous, because some matter has left and has gone to the ocean, made of clay, made of oxides, mixed with organic matter coming from above, because photosynthesis here, which was invented during the Earth history, is capturing the energy from the sun to make some organic matter out of it. And so the critical zone is this system here. And here we have the weathering front, which is the base, so to say, of the critical zone, which is diffusing in the rocky part of the planet. But it would be wrong to consider this critical zone as a static object. And what is very important in this critical zone view of the planet Earth is that it's a dynamic system. It's a conveyor belt. It's something which has a residence time. It's not something that was created and that will die one day. It's something which is it's a dynamic system, which is constantly formed at the base here by the chemical weathering reactions, and this is something which is continuously destroyed here by the forces of physical erosion. And so studying the critical zone as a thing, as an object, is primarily to determine these E and W terms, which is the creation terms and the destruction terms. And believe me or not, we are far today to know exactly these numbers for all the parts of the planet. So basically what my message today is to say that this critical zone is a very thin Earth surface layer which is formed by the interaction of atmospheric gas, water, and rocks, which is shaped by life. And this is very important to realize that if life wouldn't have been present, the Earth wouldn't have had a critical zone. And of course, it's very easy at that point of the lecture to compare, to show these two images, one of a planet with no critical zone because there's no chemical weathering, there's no water cycle, life hasn't been able to activate the formation of this critical zone, and the planet Earth, which is our planet, and which is completely, of course, different. The critical zone is a critical interface of the planet, and this is the way the National Research Council of the US defined it, and why it was important to study it as a whole, because it's providing the nutrients to the ecosystem. Think about phosphorus, and I know in CEREGE a number of people have been working on phosphorus. The ultimate source of phosphorus are the rocks, and if chemical weathering reaction wouldn't be active, then the nutrients wouldn't have been able to develop. It's important for landscape evolution, and I know some people here in CEREGE have been working quite a lot and have provided quite important papers on the evolution of landscape. The critical zone processes are the processes which are in part responsible for the evolution of landscape. Of course, critical zone processes are important to to understand water quality issues and also climate regulation, because on long time scale and even on shorter time scale, the consumption of CO2 by rock weathering and the precipitation of limestone in the ocean is important for understanding the long-term evolution of the climate. What are the scientific challenges associated to the study of the critical zone? There are many problems in studying the critical zone, again, as a system, okay, as a thing. The first one, and I'm just listed a couple of issues. It's a complex environment. Water, mineral, gases, and very different circulation paths and different transit times coexist at the same place. And this is a figure I have borrowed from Camille Boucher, which was a former PhD from CEREGE, which is now working at Geosciences in the H+ observatory. It's a figure that shows you how complicated it is when you are about to look at the circulation of water into this critical zone. So you do see on that diagram, by the way, that the critical zone is not limited to the conventional soil, but that some water can go very deep into the rocks. And actually some of my colleagues in the US, in particular Bill Dietrich in Berkeley, have proposed this term of rock moisture. Okay, so rocks are not rocks, they are fractured, and within this fractured, even very deep, you can have water which is circulating. And when you have water which is circulating, you can have reactions which are occurring, and then you can have life, because once you get electrons and protons, then you can use, life can use redox reactions to make some organic matter. So a complicated layer, and I'm going to cite here a couple of papers that I think have been very important into our understanding of the critical zone, and I like to cite this old French paper, old 2009, by Jean-Jacques Braun, which is a friend of CEREGE also, which is one of the first papers that associated geophysics, hydrological investigation, and geochemical investigation at a given site. It was at Mule-Ole watershed in the south of India, to try to understand more about this architecture, okay? Because basically this architecture of the critical zone is unknown. Another paper which is really interesting and which also connecting tectonic and critical zone science is a geophysical imaging by Claire et al., published in Science in 2015, that shows that the topography is responsible for, or can be responsible for the depth of the critical zone, because there is a topographic stress which is controlling the weathering of rocks. Okay, so this is one of the loops, one of the feedbacks which was not expected when looking at the way transformation happened in the critical zone on Earth. And finally, a paper which was published in Nature in 2020, which is a very nice paper showing that it's in Brittany. When you look at the transit time of water in the critical zone, you can clearly see that the water that resides for a very long time in the critical zone has no oxygen. And the water that, on the contrary, goes faster has oxygen because it hasn't been consumed along its pathway. And so when these two types of water mix, you have redox gradient that make possible the development of life forms. And very deep. This paper reports bacteria which are oxidizing iron at 60 meters of depth. So a deep biosphere, which is there, and it was making a lot of transformation, maybe most of the job for creating this critical zone part of the planet. Second problem is that the critical zone is a kinetic problem in terms of chemistry. You have very different timescales which are interacting with each other. And of course, you have life everywhere, as I started to tell you, which is life can be seen as a catalyzing process. It's accelerating or maybe not, decelerating in some time the processes. And this is a very, very famous figure coming from the work of Lazaga back into the 80s, which is showing the number of years it takes for 1 millimeter diameter of a given mineral to dissolve. And it's only dissolution. But of course, in the critical zone, you both have dissolution and reprecipitation of new minerals. And life is everywhere, as I told you, and life, I mean, the role of life in the critical zone is still a big issue, because a lot of people are trying to make a thermodynamic of kinetics law in the critical zone without taking into account the live processes, which are basically, by definition, so to say, out of equilibrium. And now we are starting to get a number of tools in particular, and I don't want to go into the details here, in particular, isotopes, stable isotopes, which are starting to give us ideas on the way life is, for example, looking for the nutrients, and particularly the way the roots are going exactly where the calcium, the potassium, the phosphorus is in the rocks, and try to uplift these nutrients at the surface. The critical zone, another issue of studying the critical zone is that the critical zone is spatially very heterogeneous. It's due to the infinite composition which are possible imposed by the geology, the topography, land use also, and the local climates. There is no two places at the surface of the Earth where the critical zone is the same, basically. And so I know it's a problem of saying these kind of things, because when you want to publish a paper and you say, I am studying this place because this place is specific, then your paper is immediately getting rejected because it's not global, okay? So how do we compose the globe? By a number of local studies in which all the parameters, geological, topographic, land use, climate parameters, have to be taken into account. And I'm just showing you here a couple of pictures of example. For example, you can go to Guadeloupe, which is tropical climate, but depending on the type of rocks, you will get very, very different critical zone. Here you have a very, very thin critical zone, like a couple of decimeters because you're on limestone, but when you go on the volcanic part of the island, then you get 30 meters of soft material, which is coming from the transformation of the rocks below. And finally, and this is probably something which is the most important, the fragmentation, the disciplinary fragmentation inherited from the history of science. And that before this symposium started, we talked about Humboldt. Humboldt was one of the German scientists at the time that started, I think he was a critical zone scientist at that time, but he was not aware of the different disciplines that now are, for example, written on that diagram here. You have a number of people that study critical zone without even knowing it, and which have different languages, which are not able to talk to each other. So it's like tribes which have been separated with time, and now we have the challenge of reconnecting all these disciplines to study the critical zone as a thing. And if we want to define like a Higgs boson of critical zone science, it could be, are we able to understand and model the behavior, the trajectory, the time trajectory of the critical zone, the human habitat, the Earth's skin, in response to changes in the Anthropocene. This is climate change, this is changes in biodiversity in particular. What do we know about the feedbacks? What do we know about the local loops, regulatory loops, which are going to play a role? Actually, we know almost nothing. We know now, because of the climate models, very well how the Earth atmosphere or the Earth ocean are going to evolve within the next century. It's much more difficult to say something about the way a given territory, a given place, where the people are, where the societies are, is going to evolve, because it's a complex problem which is involving a number of transformations, the motion of water, the reactions, the evolution of the soil and the vegetation, and that's really something which is difficult, on which we need to have better modeling and better instrumentation. And so land use also has a major impact on the evolution of the critical zone. And so in this consortium of sciences that I've showed here, of course, we should include the social sciences. There's no way you can study a given place without taking into account the history of the place, okay? Because most of the places in the world, at least in Europe, have been occupied by humans since 2,000 years. And so this is difficult, and we have to acknowledge the fact that when we are forming our students, usually we don't do much of social sciences, which I think is a problem, and we should educate, we should incorporate into our curricula much more social sciences, and particular environmental history. So it's a critical zone for humans, and I don't want to spend too much time on that, because I don't need to convince you that we are destroying the critical zone. The Anthropocene is exactly, I think, the destruction of the critical zone. We are able to do within a couple of minutes what natural processes have done during 100,000 years. And this is something we don't pay attention, we have no respect, so to say, for the critical zone. And this is some of the images here that are exactly representative of that human tendency to destroy his own habitat. And I like this work of David Montgomery, which computed erosion rates in different parts of the world, showing that you have, from a natural point of view, a difference between the flat areas of the world and the alpine areas of the world. And you see that the conventional agriculture is where you do have rates of erosion. Conventional agriculture, is eroding the critical zone at the rate it is eroding in alpine regions. So the action of men, of humans on the planet, is equivalent to the agency of an orogeny. This is really impressive. This picture here is one of the critical zone observatory we have in France, not far from here, in the Haute-Provence Drex Observatory, not far from Digne. And of course, this paper, which was published a couple of years ago, shows that in 2020, the mass, very simply, the mass of human-made infrastructures, human-made material is equal to the mass of the biomass. So if people are still not convinced that we're living in a very particular period of the Earth's history, this figure is a very good one. Very good one. So how we get organized? How to get organized to be much more, from a scientific point of view, how to better look at that part of the planet that we are depending upon. So we have been working, and I've spent quite a lot of time on that, on building critical zone observatories. So what are these critical zone observatories? This is places. And if you understood me correctly, the critical zone is very patchy. It's heterogeneous. So we need to go to places where we can look in details at the processes, study them, quantify them, incorporate them into models. So critical zone observatory are instrumented sites which have been chosen for their representativeness, and in particular, they have been chosen because there is a societal issue somewhere. For example, the Dregs catchment, which the figure was there a while ago, a minute ago, it has been chosen because of this problem of soil erosion at the end of the 19th century in the south of France. So basically a societal question, but a scientific problem which is not easy to solve because it's a complicated problem. In this critical zone observatory, we do long-time monitoring. And I don't need to convince you that some of the processes which are creating the critical zone, such chemical weathering, for example, are slow. And if you don't have maybe 50 years of measure, there's nothing you can say about this process. And so if you don't have long-term monitoring, you can do anything. Spatial scale can range from the parcel to the Amazon basin. Nature is taken as a laboratory, and critical zone observatories tend to explore gradients. Importantly, these places are places where all disciplines meet. So the idea of the critical zone observatory is that this is places where all the disciplines can be reconnected. And this is really what I've been working on this last 10 years, to try to find places where ecologists, geologists, geomorphologists, hydrologists, hydrogeomorphologists, and social sciences can be connected and look at the processes together. The first critical zone observatory was founded in the USA, but the program is now terminated, and Europe has taken the lead on that. So one of the ideas of critical zone observatory is a theoretical one, and I have put here the figure which was drawn by Humboldt. More than 1 century ago, Humboldt was the first to recognize that the vegetation in mountains was changing with elevation and also with on the globe. And basically, the idea of building this critical zone observatory network is the same, that we can imagine to get observatories by fixing the rock type, by changing the climate. And so by doing that, we can eventually see the effect of global warming at a site by looking at different observatories along a temperature gradient. In France, we have created the OSCAR network. So OSCAR stands for, it's not Oscar, it's OSCAR. OSCAR, Observatoire de la Zone Critique, Application et Recherche. It's a site. It's a network of sites which were already existing. We didn't create sites from scratch. We start from what was existing. And France is a country which is rich in long-term observatories, which have been funded by the different research performing organizations. I'm not going into the details here. And by making a network, we hope to make the communication between the different communities more easy. OSCAR has a global coverage. You can go to the webpage if you want to learn more about the way the OSCAR observatories have been designed and are covering the entire globe. And so in OSCAR, we have been organizing work packages that try to use this network to connect people, connect disciplines, and connect with the society. So in particular, we have a work package which is very important, which is about instrumentation and sensor development. If we compare the state of instrumentation for the critical zone to the state of instrumentation from the atmosphere, we are very late. We miss sensors of water, of soil chemistry, which can be deployed in a number of places and provide the data. So there is a big effort which is being done right now. In particular, maybe you've heard about this Terraforma program, which is a program for developing low-cost instrumentation, in particular for associating citizens to the collection of data. We also have a work package looking at the interface between data and models. We have a lot of data. We have a lot of models, but very rarely the two bodies of knowledge communicate with each other. And as I said, we really need to develop models at the local scale to learn more about the way our territories, our lands are going to evolve in a changing world. And this is really, really a challenging domain here, and I don't have time to go into the details here, but on which we've been doing a lot of efforts. Again, this is a matter of connecting disciplines. And I will finish by that. We are into an international development, which I think is very promising and is very important. But before I finish by the European dimension, please join us. OSCAR is not a club. It's open to the scientific community. And if you want to join us and to have fun with us, we are organizing each summer a summer school. This is the last one we organized here in the Strengbach Basin in the Vosges. So each of our summer schools are in a critical zone observatory, and we're doing practical work with the scientists which are working there. This fall we are organizing a German-French conference between the two networks, OSCAR and Terreno network in Germany, which are about the same themes. And we have a newsletter which has this year taken the name of Cahiers d'Oscar 2025 that you can consult on the web page. So I'm not going into that. And then I will finish by the European dimension. So building OSCAR was an interesting adventure, but it's much more interesting now to go to work at the European scale. Because actually, if you look at what happens in the different countries, all the countries have been developing sites, instrumented sites, either coming from the ecology discipline or coming from the hydrology, coming from the geochemistry, and they're all converging to like a common type of observatory. So the ELTER infrastructure has been launched 10 years ago now. It's called Integrated European Long-Term Ecosystem, Critical Zone and Socio-Ecological Research Infrastructure. And I don't have the time here to comment on that, but you do see that this is 3 communities that are mixed together. And this is historical to me. Ecosystem, ecology, critical zone, earth sciences, and socio-ecological communities, which are basically originally coming from the social sciences. So this is places which are instrumented, in which different disciplines are going to work together or have been working together. You have here the different spheres which are connected, and I don't go into the details here, but in each of the sites we are collecting a corpus of data, making it possible to cross the information on these different spheres. And this infrastructure, I cross my fingers here, is going to be launched next year or the year after, in 2027, if we got the funding, of course. So my take-home messages are, the critical zone is a scientific initiative that was born in the earth sciences, so it's coming from the earth sciences. The critical zone is a critical interface of the planet that requires our attention. This is our habitat, and this is in danger. Observing and modeling the critical zone to predict its evolution requires new disciplinary associations, new sensors, new models, new generation of researchers, new university curricula, actually. And if you look at the way earth sciences program in university are still organized, I think there is still a lot of work to do, in particular to incorporate social sciences. The critical zone needs to be studied with the stakeholders. This is important because this is the place where people live. And this requires a big effort from our scientific community. It also requires from us accepting that we're not the only one that knows something about the territory. And the critical zone is part of the Earth system, and a major challenge both scientifically and politically, is upscaling. I didn't have the time to go into those details, but of course, we are not going to multiply the critical zone observatory everywhere on the world. At some point, we need to upscale if we want to use this knowledge, this scientific knowledge, and incorporate it into the Earth system models. And I thank you very much for your attention.
So we have time for plenty of questions. Let's start with Jean-Dominique.
Could also be applied to the ocean environment. Could you comment a little bit about that? Thank you.
Yeah, so as I said, the National Research Council in the US initially defined the critical zone and applied it to the terrestrial surfaces, right? But you can extend this concept to the ocean. And you could see the ocean as a critical zone. If I took the definition that I've given here, it's a zone which is transformed by the interaction of the solar energy and the deep earth energy. And this typically applies to the continental, the oceanic crust, which is being transformed by the the circulation of oceanic water, which is receiving energy from above, etc. So, and that's a big debate I have at IPGP, because the geoscience community, they keep saying me that, why don't you put the ocean into your critical zone concept? So yes, I agree, but yes, we can see the bottom of the ocean as a critical zone also.
Yeah, thank you very much for your talk. I have two questions actually. First one is, a couple of times you mentioned that your representation of the critical zone was bad, and I wanted to know why you thought it was
what?
Bad, your representation of your critical zone.
Was bad, yeah.
Yeah, you said it a few times, so I wanted to know why.
Yeah.
And the second question is that, like, as you said, like the critical zone is, with destroying this zone much faster than it can be regenerated. And at the same time, like, we need growth, not we want, and including research, as the introduction talk said that CEREGE should grow and collect more data, etc. So how does that work, like this wheel of growing and with this critical zone that is destroying way faster than we can regenerate it?
Okay, for the first question, yeah, the first time so once a philosopher knocked on my door, not door, my office. It was Bruno Latour, which was regretted Bruno Latour, was a prominent philosopher, and he asked me one question. No, the first thing he told me that your critical zone representation is a catastrophe. It doesn't speak to anybody except the scientist. And that's true that in that audience, when I show this figure, everyone understands, okay? Because you've been educated in that, with that kind of representation. You know this vertical dimension, etc. But actually for the stakeholders, go to your, I don't know, your mayor, and think about this law, which is a zero artificialisation net, the artificialization. I mean, they don't understand these diagrams because it's static. It's describing things. It's not saying something about the dynamic of the system. Okay, so it's a bad representation. It's a good representation for scholars. It's not a good representation for talking to the society. And we need really to make efforts to get better representation. So I've been working with landscape architects. I didn't have the time to show new maps, new representation, because we really need to make an effort, and we have invented a new representation which is showing how, for example, the cycle of elements are working on the map of this new representation. So really, I mean, I think we are in an epoch of the Anthropocene where we really need to change our representation, okay? And the second part of your question was?
Yeah, how does it work? Like we are destroying this critical zone at high speed,
yeah,
and at the same time there's this wheel of always growing, including in the research area. Like CEREGE should grow and build new labs, etc. So how does that work in your sense? Like how can I combine this wheel of like growing and preserving this critical zone?
Yeah, so preserving the critical zone is I mean, we have to coexist with the critical zone. Okay, so it's a slow processes which are building it. So I think what humans need to do is to reconcile themselves with the rates of critical zone transformations, okay? And these rates are not very well known. We know, for example, we do see a tree growing and we see the leaves at fall being decomposed, blah, blah. This is something we can see. This is something we can be aware of. But when you go into processes like chemical weathering, you cannot feel chemical weathering. We're not equipped, so to say. So we need sensors. We need extensions of our sensors, so to say. And so I think we, earth scientists, we have a job to do, which is to try to better explain that the critical zone is not just a tree which is growing and falling next fall. It has several timescales which are embedded, which are nested, and that if you want to preserve the system, you need to consider all these timescales. So I do think, and that's a critical opinion I have on earth sciences, I think that earth sciences have been too absent from the ecological, debate and narrative, okay? I think we really need, and this is a job of earth scientists, to re-inject, to re-put some longer timescale into the narratives.
Speaking of sensors, could you tell us a bit about Terraforma and the kind of sensors which have been developed recently?
So it's very easy. You can Google Terraforma instrumentation, and you will immediately get onto the catalog. It's like a supermarket, and you can buy, if you want, your sensor, your favorite sensor. So I'm just kidding, but it's true. Some of the sensors are not developed yet. They are at the level of development which is still low, but people are working on it. But some of the sensors are now ready. So, for example, its sensors enable the people, the citizen in particular, to measure, I don't know, pH of the water, nitrate concentration, these kind of things. I know you're an isotope geochemist, Bruno, and you know when the measurements are very clean, very precise, and you prefer to have 10 measurements instead of thousands. I know that. But I think this is also something we need to change in our minds. If we want to equip the population, the people with sensors, we need also to be less, attentive to the precision of the measurements. I mean, this is the whole domain of citizen sciences, which is very well developed in other sciences and earth sciences, but which is something we're developing.
Thanks for your presentation. You partly answered my question. The idea is, it seems to me the big challenge when dealing with the critical zone is how to combine the different timescale at which the processes are taking place, from the second to the thousand of years. And if we want to give tracks for the stakeholders to deal with the change in the critical zone, we really need to see and try to find out how to combine these scales. So is Oscar planning to deal with this combination of time scale, or how to approach this combination?
It's a very good question. Actually, you're summarizing better than I did. The problem of representation, okay? So, in Oscar, we're working with architects, as I told you, but also social scientists, because when I make this kind of lecture on a public and an audience, which is not a scientific audience, this is exactly the question I have. How do you make people aware that what we usually consider as a picture, the environment, is something which is living, and which is living with different time scales? How can we make people aware of that dynamic? And as I said, this representation is not a good one, because it's a very static one. Nobody wants to spend time on that kind of representation. And so I don't have the new representation here with me on that presentation, but I can show you some. We are trying to make new representation, in particular incorporating the data from the low-cost sensor that we are distributing to the people. Because if you are, as a citizen, measuring something, then you want to know what the data are going to be used to, and you want to participate to a new way of representing things. You know, how the water in your catchment is circulating, how fast it is circulating, where it is going when a drop of rain is falling on the ground, etc. So yeah, good question, and this is really the challenging issue, making our the citizen aware that no, nature is not something which is fixed, something which is animated, you know, and there's probably something which is really lacking in the ecological narrative today.
In your presentation, I mean, you stressed the fact that the critical zone science is spread among many subfields, and people do not communicate. And I think it's clearly due to the history of the development of science. And it's important also to do the history of the field. And for example, I was glad that you underline, in fact, the role of Jacques-Joseph Hebelmain, so a famous, not so famous actually, no. French scientist. He died at before 40 years old, yeah. And he made many contributions to science. But it was, I mean, what he did was not only, in fact, to understand the chemistry of the formation of the clays with silicate rocks, but also he understood the tide balance. That, in fact, it was that process that was balancing the CO2 flux from volcanoes, yeah. And weathering. Yeah. And actually, his work should be even more prominent because he was the first in 1845 to underline that in the past, climate was warmer, and it was probably due to CO2. In fact, and this was the first mention of that in the literature. Yes, it is.
No, he's not explicitly saying that. He didn't know that CO2 was a greenhouse.
No, exactly. But, yeah. But there are a few sentences. I mean,
yeah.
You can read, and I collected them, but he knew that the density of CO2 was large enough to explain, and he made that hypothesis in 1845. So in effect, he was a key pioneer before all the others.
Yeah, yeah.
And it was in 1845.
Yeah, yeah.
This should be
I agree.
More
yeah. There is a paper from Bob Berner, the initiator of the global carbon cycle. Yeah, I agree. His name is on the Eiffel Tower, but not for that reason. He invented the first artificial olivines, dry synthesis of olivines. But
yeah, so thank you first of all for amazing talk. That was really inspiring, and I couldn't agree more with you that the disciplinary fragmentation is really basically the cutting edge. We have to somehow overcome that, or we have to work on that. And I mean, we're all kind of looking into basically the survival of the human species on Earth, and this disciplinarity is in big time in the way. And I also totally agree that we are awful in presenting our work, and so that is kind of the new ways of communication is really absolutely key. So my question is a technical one. So obviously you need to work in a mega transdisciplinary team across all the disciplines, and you probably run, as we all do, into limits of the funding system. So how do you navigate that? How do you get a program funded that includes architects, social sciences, whatever, psychologists,
Yeah, it's a very complicated problem, and I can tell you one story. We applied to, in France we have this big program called PEPR, which have been a lot of money injected into the science system. So we wrote a proposal, a big one, for applying to a PEPR, which is called Transform. Transform, basically saying that we need to transform the way we look at the habitable part of the planet and have a multidisciplinary approach. And basically, so the international jury said it was a very beautiful program, it has to be done. So it was associating science, arts, and social sciences also. But then the Ministry of France said, we don't really understand what you want to do. Okay, and so we got this new early July this year that the program, which was initially funded at the level of 50 million, will be funded at the level of 15 millions. And then in 2 years, we need to come back and show what we did. And this is a typical process, you know that, in the funding, by the funding agencies. But to me, it shows something. It shows that the funding agencies are not ready to see what we want to do. And that's not a good sign, you know. This is the fact that, I mean, at least in France, the funding is still very, very disciplinary. And at the Agence Nationale de la Recherche, the French NSF, you have a branch which is doing, how they call that, participative science, for example, but it's, you know, peanuts compared to the other programs. So this is not good science. And what is happening on a global scale today in the US, but also in other countries, is not also a good sign. I'm not sure we're going into the good direction. I'm sorry to say that.
Yeah. Thank you very much, Jérôme, for a fantastic talk. I have a question. You said that the critical zone observatory that are in network in the OSCAR are driven, the choice of those observatory are driven by societal issue. So how does it work? I mean, is it something coming from the territory that made you choose one area? So is it like coming from, you know, citizen that
it's a good
goes
question.
to you, or the question with this is that you said that each observatory is specific, but we have to do global with specific, and at the same time there is this issue of financing. So do you think that the territory level, you know, driven by those societal issue is some path, or? So yeah, what do you think about that, and how do you do?
The answer to your question should be looked at each observatories, because each observatory has a different history. But if I take one I have in mind here, which is a critical zone observatory in the Vosges Mountains, it was launched because of the acid rain problem. Remember, in the 90s, we were not talking about climate change. We were talking about acid rain problems in Europe. And at that time, a couple of scientists from Strasbourg University decided to launch observation that they wanted to be long-term observation in a particular catchment in the Vosges Mountains, which they thought was representative. And 40 years after, we're still doing measurement on that site, and we've learned a lot. I mean, we've learned a lot the way the ecosystem, the local critical zone, has responded to the improvement of the atmosphere at that place. So each of the observatories have a specific history, but it's interesting. I don't have really a clear explanation to your question, but it's interesting to see that at the beginning, it was a societal question. Like in the Haute-Provence, the erosion, which is drastic, we have passed a tipping point in the erosion. I mean, these soils will never come back to the previous state they were in at the 18th century, never. So we have a tipping point. And so this is interesting that all these observatories have been led, motivated by a societal question. And then the other part of your question is really a tough one, which is how do I do from that local observation, how do I upscale? And actually, because I'm now working with a lot of social sciences and political sciences, this is a problem that all these sciences have. How do you do a politics from the local? How do you pass from the local scale to the national scale? This is exactly the problem we have. So we have a number of tools now enable us to use the results obtained at the local scale to upscale them, like modeling, for example, or satellite imagery. But this is still a challenge. And actually, I was at the Goldschmidt conference early July, and I'm always very surprised that in our communities, and that's a self-criticism, we all put on the same diagram very small things, like a very small stream in the Alps and the Amazon. And we try to tell a story about this, comparison. I think this is not a good approach. It's like if you compare, the politics of your small village to to the politics of a state, you know. And so I think this is really a scientific challenge for our disciplines to work better or to be better aware of how to upscale these processes. But yeah, it's a tension. We are not going to cover the whole planet with critical zone observatory. This is just technically impossible. So one clue is that gradient issues, you know, which is highly criticized. We could have a debate here the whole day on whether this is interesting to make these gradients or it's bullshit ideas, you know. But this is one way of trying to upscale the processes. Yeah, but it's a tough question.
Okay. Well, thank you again.